Good afternoon to you all for the 8th week's lectures on fluid dynamics and turbo machines. In the last week, we have discussed about the hydraulic machines, and in this week we will take up the steam and gas turbines. As I have mentioned in the beginning of this module on turbo machines, that the steam and gas turbines come under the classification of compressible flow machines or machines that handle compressible flows. In the fluid dynamics module, Dr. Bakshi has talked about the incompressible flow. So, today what I will do is I will give a brief introduction to compressible flow. Please note that this is only an introduction which is necessary to better appreciate steam and gas turbines. This by no means is a complete lecture on compressible flow. For that you should refer to specialized courses and textbooks on compressible flow. So, let us first take the physical example of this compressible flow. You have already studied in fluid dynamics that fluid flow can be compressible or incompressible, and you have also learnt that the Mach number the fluid flow should be less than 0.3 in order to treat the flow as incompressible. We will know this we know these things, and we will talk about some more aspects of the compressible flow in today's lecture. First, we will start with wave propagation through compressible media. We should note this term compressible media. In reality, there is no medium which is completely incompressible. A medium which is completely incompressible in that the speed of sound, as we will show it, will go to infinity, but all the fluid medium, the solid medium, whatever we can think of are compressible. Only the extent of compressibility, as was discussed in the module A, will vary from gas through the liquid to solid. So, when we talk about wave propagation through compressible medium, what we have to keep in mind is that we will have a finite speed of the disturbance or finite wave speed or sound speed. So, how do we understand this? Let us say we have a long channel which is filled with fluid initially at rest, and we have a piston, and that piston suddenly starts to move. So, we give this piston a small infinitesimally small velocity d c. C, as you have already been aware, in this module we have used it to refer to any velocity. Now, if this medium had been an incompressible medium, an idealized incompressible medium, the moment the piston is set into motion with this d c, this disturbance would have propagated through the entire fluid, and the entire fluid should have been in motion. But because it is a compressible medium, so what will happen is the fluid far away from the piston will still be at rest. However, the fluid near the piston will start acquiring the velocity, and then this information or the disturbance that there is a small velocity d c being imparted by the piston will propagate, and we can say that this disturbance propagates as a wave with the speed of sound c s through the medium. And you can see that for the left of the fluid from this wave, this region as shown here is already under the influence of the motion, whereas the fluid to the right is actually at rest even at this instant. Next instant you can see that this wave would have come to some other location. Now, if we want to analyze this flow from this stationary frame, then what we see is this is an unsteady flow, because at one instant this region which is shown between the solid wave and this dashed wave lines, it was in rest, and then after this wave has passed, then we find that this would have also experienced the motion. So, in order to analyze this problem, we can try to frame it in a slightly different but equivalent way. we can say that this is the same long channel and we fix our axis systems x and y and we say this is the wave. Now, however, we make the wave as stationary and we impart a relative velocity, that way the fluid to the right moves to the left with a velocity c s and the fluid to the left, which was already under the motion because of the piston, will have a velocity c s minus d c. d c, I remind you, is the motion or the velocity due to the piston. Now, the fluid which is downstream, which is now to the right, will have these undisturbed pressures P and rho, and fluid to the left, which is already under disturbance, will have a pressure, let us say P plus d P and rho plus d rho. Please note once again that the x direction in for this picture is from right to the left. Now, we can apply the conservation of mass across this control volume and we can say that rho times C s times A is the area of the passage, is equal to rho plus d rho multiplied by C s minus d c multiplied by A. Now, area, it is a constant area duct, constant area passage, and hence the area gets cancelled. So, we are left with rho C s is equal to rho plus d rho multiplied by C s minus d c. Now, we can open these brackets, multiply the cross terms, that is rho C s minus rho d c plus C s d rho minus d rho d c. We can do that and we can neglect the second order terms, that is the term which contains the d rho d c. If we neglect the term d rho d c, because these are going to be small, we have assumed that d c is an infinitesimally small change in the velocity, and then we can say that the corresponding small change in density is d rho and hence their product will be much smaller. So, this is a very standard practice in analytical expression, deriving analytical expressions in mechanics. So, we can now simplify, because we know that rho C s gets cancelled from both sides of the equation, and finally, we end up getting that rho d c is equal to C s d rho. This is what the mass conservation or continuity equation gives us. If we now do the momentum conservation, we should note that on one side we have pressure P acting, on the other side we have a pressure P plus d P acting, but the area is same and we know that the rate of change of linear momentum is nothing but the force. So, if we go for the conservation of linear momentum, then we know that sigma f x, which is the summation of all the forces, is equal to m dot C 2 minus C 1. 2 is downstream side to the left, 1 is upstream side to the right according to this figure. Please keep the figure in mind, and the forces that are acting along positive x is P A, the force that is acting along the negative x is P plus d P multiplied by A. We have not considered any friction, so fluid friction does not arise here. And then we can say that P A minus P plus d P multiplied by A is rho C s multiplied by A, that is the mass flow rate. Rho C s multiplied by A is m dot and C 2 is nothing but C s minus d c and C 1 is C s. So, once we simplify, we get that minus d p, see the first term gets cancelled, P A with this second term which is inside the first term of the bracket gets cancelled and we get minus A d p, and we have A on the other side. So, A gets cancelled. So, we get minus d p is equal to minus rho C s multiplied by d c, and we already know that rho d c is equal to C s d p. So, let us substitute rho d c in and put it as C s d p, then we will get that d p is equal to C A square d rho, and hence we can write that C A square or the speed of sound square is equal to d p d rho, or we write in the usual way that C S is under root d p d rho. Now, we cannot evaluate this expression d p d rho unless we know what is the thermodynamic process. And to get an idea to this thermodynamic process, particularly the one that we are dealing with here, let us try to recollect what are the assumptions we have made. We say that there is only an infinitesimal change across the wave, which is caused by an infinitesimal velocity change in the piston d c, and the process may be assumed reversible. We are not talking about any friction and there is no heat transfer. Hence, we can consider the change to be isentropic change or reversible adiabatic change. And so, we now know the relationship of how the pressure varies and the density dependence. So, we can then substitute for perfect gas that C S is under root gamma R T, and the usual value of 332 meters per second for air at STP can be obtained. If we think about the liquids or gases or solids, the another way of talking about in terms of liquids and solids is in terms of bulk modulus, and we can say that the C S is nothing but under root k by rho, where k is the bulk modulus of the medium. And then we get that, for example, for a solid like copper, it is 3722 meters per second. So, what we get? We find that the more compressible the medium is, the more easily the medium can be compressible, the speed of sound is less. And it can also be shown that for an ideal incompressible medium, there is no change of density, and hence we will have the speed of sound going to infinity. We have discussed this with respect to the straight passage. Now, what happens is, in case of steam and gas turbine flow passages, the passages will have varying area. So, the blades will produce the blade passage areas which are continuously varying. Of course, that is a complicated geometry. So, what we will discuss here is what is the effect of an isentropic flow through a channel of a simple varying area as shown now. So, we are talking about a flow from left to the right, and hence we call these structures as diffuser. We could have done this similar analysis with the flow area reducing in the direction of flow. In that case, we call it a nozzle. So, for this geometry, whether it is a nozzle or a diffuser, it does not really matter. We assume the same like we have done for the straight passage, that we are assuming an isentropic flow. That means, there is no question of fluid friction or viscosity and there is no heat transfer. So, reversible adiabatic flow, and we take a control volume. We write down the variables, the flow variables. To the left is C, rho and A. C is the speed, rho is the density and A is the area at that location. On the right side, what leaves is C plus dc. The corresponding density of the fluid is rho plus d rho, and the area of course has changed. This is a difference from the previous example we took of a straight duct. In this case, the area is not constant, area becomes A plus dA. So, if I take this control volume out and try to find out the force. So, the force on the left which is acting in the flow direction, the flow direction in this case is from left to right is my positive x direction, and we can say that the force acting on the left area is P times A. On the right, the force acting is P plus dP times A plus dA. Also, there will be a force acting on the additional area which is on the sides, and since it is a very small area length dx we are talking about between the left and the right ends of the control volume, we can approximate the pressure as P plus dP by 2. So, the force that acts on the surfaces on the slant surfaces is P plus dP by 2 multiplied by dA. So, we can do the conservation of mass like the way we have done for the last time, but here please note that the area is not constant. So, we can say that rho C A is the mass flow rate entering the control volume, and rho plus d rho multiplied by C plus d C multiplied by A plus d A equal is the mass flow rate which leaves the control volume. And for a steady flow, you know that rho C A must be equal to the what leaves from the right side. Now, no mass can leave from the slant surface because wall is present. So, we can follow the similar analysis of expanding these brackets, arranging terms which are higher order and dropping those terms, simplifying terms and removing terms which can get eliminated. And once we do this simplification, I suggest that you do this simplification as well parallelly. I am not doing all the steps. So, if you do the simplification, you should get that d C by C plus d A by A plus d rho by rho equal to 0. You could have got this relationship simply from the fact that rho C A is constant. You could have taken log and differentiated and you will get the same relationship, but here I am doing from the control volume approach of the first principle. So, the mass conservation for an isentropic flow through a channel of varying area gives me d C by C plus d A by A plus d rho by rho equal to 0. The conservation of linear momentum then will yield that P A plus P plus d P by 2 multiplied by d A. Please note that P A acts from on the left surface. So, it is acting on the direction of positive x, and so is P plus d P by 2 times d A. Whereas, P plus d P which is acting on the right face is acting in the negative direction of x, and hence this sign comes as minus. So, we can say that the total force acting on this control volume is P times A plus P plus d P by 2 whole multiplied by d A minus P plus d P whole multiplied by A plus d A, and that must be equal to the rate of change of momentum. So, rho C A as before is the mass flow rate, and the velocity on the right hand side when it leaves is C plus d C, and the velocity with which it enters the flow enters the control volume is C. So, we can say that rho C A multiplied by C plus d C minus C, and we can simplify this left hand side and the right hand side, ignore the second order terms, and when we simplify we get that d P plus rho C d C equal to 0. This result is important, and we can rewrite this expression as d P by rho C square plus d C by C equal to 0. Why am I doing it? Is because I have a term d C by C in the mass conservation, and I am trying to eliminate one of the terms. It need not be that we can eliminate d C by C, we should eliminate one of the terms. So, here I find that d C by C can be written in terms of d P rho and C square, and this is what we have got d C by C plus d A by A plus d rho by rho equal to 0 we have already obtained from mass conservation. So, if we now use these two relationships and eliminate d C by C from them, what we get it is minus d P by rho C square, which is my d C by C term from here, plus d A by rho which is coming from the mass conservation, plus d rho by rho equal to 0, or we can write it as d P minus rho C square whole multiplied by d A by A plus d rho by rho equal to 0. Let us see what we can get from here if we move further. We can write this same expression again in the next slide. I write that d P minus rho C square whole multiplied by d A by A plus d rho by rho equal to 0. This is essentially the same expression which I have derived in the last slide. And we know that the speed of sound is given as c s square is dp d rho. And we can now club these two relations, that is the one on the left hand side which we got from momentum conservation and the speed of sound, and then we can say that dp minus rho c square dA by A remains. We now replace d rho and write it in terms of dp. So, we get that dp by rho c s square equal to 0, and once we write it, we can club the expressions which are connected with dp together, and we get that dp whole multiplied by 1 minus c square by c s square is equal to rho c square dA by A. Now, c by c s, as you know, is Mach number. This was already covered in the fluid dynamics module of these lectures on fluid dynamics and turbo machine. So, I replace the c by c s as Mach number, and hence c square by c s square as Mach number square, and I get that dp times 1 minus Mach number square is equal to rho c square dA by A. We will now take special cases of Mach number less than 1 subsonic flows and Mach number greater than 1 supersonic flows separately. First, we start with Mach number less than 1, and we can have two situations. The first situation can be the flow in a converging passage or nozzle. We can also discuss the flow in a diverging passage or diffuser. First, let us look at a subsonic flow through a nozzle. In the direction of flow, this direction of flow is given by the blue arrow. In the direction of the flow, there is a reduction in the area. Converging passage or nozzle has a reduction in area. So, this reduction in area implies that dA, this term dA here is going to be less than 0. Now, if dA is less than 0, what will be the sign of dp? 1 minus Mach number square for Mach number less than 1 is positive. So, that means the sign of dp should be the same as the sign of dA, and hence we should note that for this case dA is less than 0, which means dp is less than 0. And if we had eliminated pressure and written in terms of speed, then we could have written it as dc by c times Mach number square minus 1 is equal to dA by A. I told you that you can eliminate dc by c, or you could have done it dp by p. So, now we have removed dp and we are substituted in terms of dc. So, if you look at this expression, this bracketed term Mach number square minus 1 is less than 0 for Mach number less than 1. Now, this is negative, dA is also negative, that makes dc to be positive, and we get an accelerating flow in the nozzle when Mach number is less than 1. This is our usual experience, of course. When we take a diffuser, the scenario just reverses, because we have area change positive in the flow direction, area has increased, which means in the relation connecting dp with dA, dA is positive and hence dp has to be positive, and in the relation connecting C with A, we find that dc has to be negative, and hence the flow reduces or decelerates for the case of a diffuser in a subsonic flow. The situation changes if we go for the supersonic flow. Let us look at it again carefully. Let us have the same expressions in front of us which we have done in the last slide. So, dp into 1 minus Mach number square is rho c square times dA by A, and dc by c times whole multiplied by a Mach number square minus 1 is dA by A. But in this case we are considering Mach number greater than 1, and we are considering a convergent passage and a divergent passage. For Mach number greater than 1, for the pressure relationship we have this bracketed term as negative, and for the convergent passage dA is also negative, which makes that dp is greater than 0. For the diffuser, the opposite situation prevails and we get dP less than 0. So, we can say for Mach number greater than 1, a converging passage acts like a decelerating flow passage, the speed reduces, whereas a diverging passage or a diffuser acts like a accelerating flow passage and the pressure reduces. So, now if you have to construct a geometry in which you want the flow to continuously increase from subsonic to supersonic, how will you do that? You can also keep in mind that if Mach number is equal to 1, we get no change in area, because if Mach number is 1, then you see dA by A goes to 0. So, we should have a flat region. This is shown here. So, in this case the flow starts from the left with the arrow shown here. The flow is initially subsonic, and as we have discussed just now that in the convergent passage the flow will accelerate and reaches the straight portion which is called the throat. This arrangement of a convergent portion followed by a very narrow or short straight portion and then a divergent portion is called a CD nozzle or converging diverging nozzle or D level nozzle. Now, this nozzle or CD nozzle, to be more precise, is used in steam turbines, for example. Why? Because what happens is, in a convergent passage you cannot exceed Mach number of 1. At the most what you can get it is a sonic velocity at the throat or the minimum region area, minimum area portion. But having connected a divergent portion, it is possible that the velocity can accelerate and we get Mach number less than 1 in the convergent portion, Mach number equal to 1 in the throat and Mach number greater than 1 in the divergent portion. And hence, in the steam turbine, as we will see in the next lecture, the CD nozzle is used to accelerate the fluid. In the absence of work and heat interaction, it was shown earlier that H 0 is equal to constant, which is the stagnation enthalpy is constant. We have discussed this as an example problem in thermodynamics when we talked about flow in a nozzle or a diffuser. So, starting from there we can say H 0 or the stagnation enthalpy is nothing but static enthalpy plus C square by 2, which can be written in terms of temperature assuming Cp to be constant as T 0 equal to T plus C square by 2 Cp, and we can write that T 0 by T is 1 plus C square by 2 Cp times T. So, what does it lead to? Let us look in the next slide. We know that we have already just found out that T 0 by T is 1 plus C square by 2 Cp T, and we know Cp is nothing but gamma r by gamma minus 1. These relationships you know from thermodynamics as well. So, if we now combine this, we can get that T 0 by T is 1 plus gamma minus 1 whole divided by 2 times C square by gamma r T, and we can replace gamma r T as C a square or speed of sound, and hence we get ultimately that T 0 by T equal to 1 plus gamma minus 1 by 2 times Mach number square. When we connect pressure with temperature, then we can say that P 0 by P, the corresponding stagnation pressure is P 0 by P is equal to T 0 by T whole to the power gamma by gamma minus 1. And when we substitute T 0 by T as we have got just now, we can write that P 0 by P is 1 plus gamma minus 1 by 2 times Mach number square whole to the power gamma by gamma minus 1. And we can also say that in the limit of Mach number being very low in the incompressible flow limit, you can show, I leave it as an exercise for you to show that P 0 is nothing but P plus half rho c square. Try to prove it yourself by taking that Mach number is very small. I leave it to you as an exercise and show that Mach number in the limit of small Mach number or low values of Mach number, you will get the incompressible flow relationship connecting stagnation pressure and static pressure. We can also do a quick check on the comparison of isentropic and adiabatic processes. So far we have discussed only isentropic processes, we have not considered any friction. I am not going into details of what the friction can bring about, because that is a lecture in itself, and one can see this in advanced books on compressible flows or fluid mechanics. But here what I am just trying to show you an aspect of the pressure and temperatures for isentropic and adiabatic processes, which is going to be useful for better understanding of the steam and gas turbine. So, we say that it is an adiabatic expansion in a nozzle. 2 is the nozzle inlet. You remember we have talked about that higher the number we assign, the higher is the pressure, higher is the enthalpy. So, nozzle inlet as higher pressure, higher enthalpy, there is an expansion. So, we have given it the number 2, number 1 is given to the nozzle exit. 1 is, to remind you, is nothing but the ideal or isentropic expansion in the nozzle. 0 2 corresponds to the stagnation state, 0 1 corresponds to the stagnation state corresponding to nozzle exit. So, we know that H 02 equal to H 01, we have got it from the first law of thermodynamics. But if we consider now two cases, isentropic and adiabatic, that is with friction and without friction, but both without any heat transfer, then we can say that without friction, in the idealized case, the expansion should have taken place from 2 to 1 s. However, due to friction, due to irreversibilities, then we get it from 2 to 1. And from the first law we have said that H 02 equal to H 01. If there is an ideal gas, then we can say for the perfect gas T 02 equal to T 01, and this is shown here in the horizontal line. But you also note that the pressure, the point 02, the state 02 lies on a pressure P 02, which is not same as the P 01. We find that P 02 is greater than P 01, that is because there is a drop in pressure because of friction. So, we have to consider these effects, and later on when discussing the steam and gas turbines, we will define a nozzle efficiency to account for this non-isentropic or adiabatic cases involving steam turbines. The next thing that we need to know is compressible nozzle flow and choking. So, let us say that I have a reservoir here. In the reservoir, the velocity of flow is 0, pressure of the in the reservoir or the tank is P r, and the temperature is T r. Since the velocity is 0, you can take that as an stagnation values, and this tank is connected to a convergent passage, and then we have the back pressure P b. This P e, we are distinguishing between P e and P b. P e is the pressure at the exit of the nozzle, and we will soon see why P e needs to be different from P b. So, let us do a thought experiment first. We say that there is a this reservoir connected to a back pressure environment and by a nozzle. Initially, let us say that the P b or the back pressure is kept same as the reservoir pressure. Reservoir pressure does not change in this entire thought experiment that we are going to do. So, we keep reservoir pressure as P r and we will gradually reduce P b. So, when we say that we have P r equal to P b, there will be no flow, and flow by the way will take place in the direction x shown here. So, if I want to vary pressure with x starting with P equal to P r, then in the first case I get there is no change because there is no flow. Now, let us say we start reducing P b gradually. Once we do reduce gradually, there is no change here because this is the tank portion, and then the pressure reduces, and at the exit P e is equal to P b. We continue reducing P b further and we get the curve C, where again P e is equal to P b, and D P e is equal to P b. And then if we reduce P b further, what we find is that the flow rate does not increase anymore. The flow rate was increasing as we reduce pressure from P b at A to P b at D. But if we reduce pressure P b beyond D, what we will see is that there is no increase in flow rate and the pressure P e is not equal to P b. What will happen to the flow is that after reach the exit, there will be an expansion wave. I will not go into details of this expansion waves. There will be an expansion wave and then the flow will adjust the pressure P b at some distance downstream, which is given by the line E. So, if we want to now draw the mass flow rate versus the pressure ratio, that is P b by P r, we can show it like this, that mass flow rate m dot versus P b by P r starts from 0 when P b by P r is 1 and it gradually increases till D as we have discussed, but beyond D the line is straight horizontal, which means it does not depend on this back pressure. So, D and E have the same value and the flow at this D is called the choking flow. So, how do I get the state D? What is the pressure ratio at D, that is what is the critical value of P b by P r? If we reduce the pressure ratio less than this critical value, the flow is choked, there is no further increase in mass flow rate. To get that, we need to look into the relationship we have derived earlier between the stagnation pressure and the static pressure, and we can write that P 0 by P is equal to 1 plus gamma minus 1 by 2 Mach number square whole to the power gamma by gamma minus 1. And in this case, please note that P 0 is nothing but P r and P we are referring to P b. So, then we can say that P b by P 0, which is P b by P r, will be equal to 1 whole divided by 1 plus gamma minus 1 by 2 Mach number square whole to the power gamma by gamma minus 1. But in this case, the Mach number becomes 1, because we told you already that in the convergent portion the highest speed that can be attained is corresponding to Mach number 1 at the minimum area or the throat. At the throat, the highest speed that can be obtained from a subsonic condition through a convergent passage is the Mach number 1 or the sonic state. So, if we put Mach number 1 here, then we get P b by P r for the critical case as 0.5283 if we use gamma equal to 1.4. So, how do I understand? This is giving me a mathematical way. How do I understand physically? Let me tell you a story. Let us say that you are sitting inside this reservoir and you are going to allow the flow to increase, and your friend is sitting in the back pressure here in this portion. The moment every time he shouts, you increase the flow rate, and the flow rate, the speed increases, and your friend shouts further, you increase the flow rate, the speed increases further. What will happen is, once the speed reaches the speed of sound, once the flow reaches the speed of sound, you will not be able to hear your friend's voice. And then what happens? No matter how much or how many times your friend shouts, you will not increase the flow rate. So, what happens is the same physical phenomenon is happening in this case. This pressure reduction, the Pb, is like a disturbance, and let us assume for the time being that the Pb is gradually reduced every time. We are reducing it slowly and gradually by a small amount, and this is like a disturbance we have talked. So, the disturbance can propagate at the speed of sound, but now the flow has also reached the velocity of sound. So, what happens? Relative to the flow, the disturbance cannot move upstream, and the disturbance that is set in the back enclosure will not reach the reservoir, and hence there will be no further increase of flow rate. This value, the maximum value that the flow rate gets, and we get a flat curve in the m dot versus Pb by Pr curve, is called the choking condition. So, D is called the choking condition. Now, what we will look into what happens if we have a compressible flow not through a convergent nozzle, but through a CD nozzle or converging diverging nozzle. Description is essentially the same. We have a reservoir and it is connected instead of a converging nozzle in a converging diverging nozzle with some back pressure Pb, and we want to do the same exercise of finding out pressure versus x, that is a distance. We can say mark the region for the throat and mark the region for the exit. Initially, we start with reservoir pressure same as the back pressure. I am sorry, I should say back pressure same as the reservoir pressure, because reservoir pressure does not change. What I am changing is the back pressure, and hence we get that there is no flow. Once we start reducing, as I have done in the last case, the pressure reduces and then starts increasing. This is still a subsonic state, and then we get a critical point which is the sonic throat. In case of B, the sonic speed has not reached in the throat. In case of C or G, the sonic speed has reached, but the pressure at C, the back pressure corresponding to the curve C, is such that the flow takes a subsonic flow, and we get the upper limb of this curve. In case of G, the pressure is such that you get a supersonic flow in the diverging passage. In both cases, the pressure at the back pressure corresponds to the critical pressure, which is P c, corresponding to C I have given, and the sonic throat is reached, sonic throat condition is reached. But what happens if we have a pressure or back pressure ratio lying between the curves C and G? If the pressure is between C and G, then what will happen is the flow will continue in the supersonic regime, this curve along G, then it comes here and tries to adjust the pressure. Now, you know that a supersonic flow in a divergent passage is always going to accelerate, and it can never give you, for an isentropic flow, I repeat, it can never give you a pressure increase. We have just now seen that if Mach number is greater than 1, then if dP times 1 minus Mach number square will be related with dA by A, and if area has increased, dA has increased, then dP has to reduce, because 1 minus Mach number square is going to be negative. So, that means the pressure should reduce, which is exactly what the curve G gives. But since we want a pressure which is higher than Pg, so what happens is this isentropic flow condition breaks down and we get what is known as shock. So, this curvy line is my attempt to show a shock stands there, and then we get the pressure adjustment. If you reduce the pressure Pb further, the shock travels downstream, and instead of D we get the shock at E, and then the pressure adjusts. This process will continue till you reach the shock at the exit, and then the shock no longer remains a normal shock. We are not going into details of shock and the expansion waves, as I have talked about earlier, because in this course what we need is to appreciate the fact that a CD nozzle or converging diverging nozzle is essentially useful to bring me a higher velocity than what a simple converging nozzle can give. And if the pressure is below G like H, then what will happen is the pressure will be adjusted by the form of expansion waves. For details about this, you should see a good book on gas dynamics or compressible flows. So, with this I come to a conclusion for the introduction, a very brief introduction to compressible flow. We talked about the wave propagation through a compressible medium. We have talked about the isentropic flows through varying cross sectional area passage and found out the relationships connecting the change of pressure, change of area and change of speed. Most notably, we have noted that unlike in an incompressible flow, in compressible flow a nozzle or a diffuser can give rise to a change in velocity in either way. That is, in an incompressible flow, whenever we see a nozzle, we know that the flow should accelerate. Whenever we see a diffuser, we know that the flow decelerates. But in case of a compressible flow, we cannot conclude so simply. We need to know more, we need to know the Mach number. So, Mach number less than 1 will behave in the same way as in compressible flow. We will get a convergent portion for flow acceleration and divergent portion for flow deceleration. Reverse situation arises when Mach number is greater than 1. And a CD nozzle in particular is useful to get a very high velocity coming out of the CD nozzle that can go into the rotor of steam and gas turbines. That discussion on steam and gas turbines will be taken up in the next lecture in this week, and with this I conclude. Thank you.